Okay, and we're COMP100. It's week 3, lesson 3, part 3. And we just talked about connected to GitHub. We talked about, I created this Dropbox for you guys so you can connect there. And we talked about Visual Studio and some of its attributes, different screens and what they mean. So basics, right? We haven't done anything with Visual Studio yet. And I just wanted to get you guys comfortable with creating a project and what it all means to do that. Let's go to the left here and start off with our first intro into the world of programming. So this officially would have been lesson 2, so I'm kind of fast tracking you guys. Like I said, I would have talked a little bit more during lesson 1, setup and all that kind of stuff. But you know, time being what it is. By the way, these lessons, and I've got this lesson right here. You're still not in it. Which one?
One you're using to show us. That's not Mac, but it's on Windows.
It's Mac.
Yeah, what's the program called?
PowerPoint. I'm going to. That's okay. That's fine. I'm going to upload my presentation here, lesson 1, in the lesson 1 folder I created. So I'll do that at the break. So I'll put my. Actually, you know what? I'll do that now. Just cause. So I'm going to kind of go into my Centennial, and I'm going to log in, go to eCentennial, hit your course, which is number 80, and go into my content section and into lesson 1. I'm going to, actually it will be lesson 2. Lesson 1 will be blank, which is good. I'm going to upload my files into there, and the first one I'm going to upload is from COMP100 lesson 1, lesson 2 I mean, which is this PDF document. And it should be
lesson 2, but it's lesson 2, but it's technically lesson 1.
Correct. Well, actually, lesson 3 is technically our lesson 1. So I'm just going to put it up there. So lesson 2 is the folder for lesson 2 is what I'm going to be looking at. It says lesson 1, chapter 1, right? Also in lesson 3, so it allows you, if we don't get to it today, just so you can read ahead, right? If you don't have the book, I'm going to put up the PowerPoint presentations for that lesson as well, right? Because I want you to be able to look ahead, and that would be under data, which I'd like to try and get to as much as I can. You cannot. It's impossible. You can't skip any lesson. Every one of them is important. Okay, so this is lesson 2. And lesson 1 is empty, it's blank. This is just that would be our intro lesson. Inside there, I'm also going to create a link to GitHub. I won't do that today, but I'll create a link for my playlist for these videos that we're doing right now, right? So you can link to them, and if you need to watch them or review them, you can do that if you forgot something.
Are you going to put the course
outline
up?
Eventually. Yeah, we'll do that too. Okay, so so we've done all these things. So you should be able to see if you want to follow along with me. And this, instead of watching up here, if you want to watch in front of you, you can go up on, I don't know if you guys can do that right now, but if you go to eCentennial, you can pull down this PowerPoint presentation, or actually look at it online. And you can also read it whether we're here together or not. Now this PowerPoint presentation has 52 slides, right? Usually we can go through fairly quick at a pace at about a slide a minute, slide every couple minutes. Sometimes I go a little slower because it's the first time you've seen this material, and then, you may have some questions. So I want to make sure I answer them for you. So let's talk about our objectives with this thing. We want to learn about programming in general. We want to talk about the difference between procedural and object-oriented programming, and there is a difference, right? What that all means. We're going to be talking about features of object-oriented programming languages, the C# programming language in general. We're going to write our first C# program that produces some kind of output together tonight, right? And we're going to learn how to select identifiers, variable names, and what variables are, and all that kind of stuff. We're going to talk about comments, what comments mean, and also the command prompt itself in Visual Studio. I'm going to look at it, but we're not going to actually do anything there, okay, through the command prompt. I'm not going to ask you to compile anything. It's all going to be through Visual Studio, okay? So let's talk about programming a little bit. So again, a very basic, high-level computers 101. Programming language is a set, or computer program is a set of instructions that tells the computer what to do, also called software. And the original programs way back in the day when I learned, and I've been programming since I was 10, right? I'm an old guy, so it's probably more, many, many more years before you guys were all born, right? Anyways, my first program I learned to program in was assembly language or machine language back in the day. And that was a series of ones and zeros. Like literally, there was no words when we programmed. We programmed in an environment where it was only an editor, right? And we could see the machine code. And the machine code in certain places meant certain things for us. There were some short codes that we would look at, but every time we created we would use a memory location and shift values in different memory locations to do stuff. That's how odd it was. So machine language back then was the lowest level language. It's the language that speaks to the machine itself. And it's a collection of ones and zeros in a certain pattern that tells the machine what to do. The machine at the very lowest level absorbs the ones and zeros, reads each one and zero, and it means something. Each byte of information, right? It depends on the kind of machine. It's 16 bits or 32 bits, each byte, right? Is going to mean something, like a little word or a letter. And they put these 16 zeros and ones together, or 8 zeros and ones together at the very minimum to represent letters or numbers, right? So you can imagine for a whole book, like a Bible, as an example, many thousands upon thousands of zeros and ones that the machine interprets to mean something. Similarly, when we program, we don't program at the machine language level, right? We want to affect this. There's two kinds of software. There's system software, like your operating system, Windows, Mac OS X as another example, and Linux. Those are the three probably most common operating systems out there right now, right? We use computer programs to do different kinds of programming. We can program operating systems, the host program, control program, if you will, that allows you to run other programs. Like, for example, we're running Visual Studio. Visual Studio is a software application that's run on top of Windows, right? Windows being the program we call an operating system that's been written by developers, right? At its base level, Windows or Mac OS X or whatever controls the hardware that's on your system in front of you to display certain things. Most operating systems utilize something called a user interface, where you can see like a window, you can move your mouse around and all that kind of stuff. Back in the day, there was nothing like that. There was no mouse, right? There was no Windows. There was just the console, which is like a little line that says, enter your command here. That's it, right? And you had to know what to put in. We're going to look at something like that. Command prompt on Windows is very similar to what it was back in the day when we first started programming at a very base level.
So all you had was command prompts?
That's it. There was nothing else. There was actually not even a window. There was no UI. And many programmers today, if you go back in the day when I talk about this, and this is way back when the computer, like the computers that we have today, the computer in my watch, right, is more powerful than a computer, that took up many, many rooms, as an example. The computer in our phones, our iPhone 6s and whatever else you have, they're more powerful than whole office buildings of computers back in the day, right? I'm talking about combined.
Can you give us a year so we can...
Well, for me, right, I started programming when I was 10, so that was 1979. Yeah, back in the day. That was 2 years after Star Wars came out, right? And Star Wars 2 came out in 1980. So it was way back in the day. I told you I'm an old guy. Anyways, so back in the day, we had these things, and there was no UI at all. And there was no mouse. There was just a keyboard and a big monitor, probably half the size of my desk, right? That's how big they were. There was no flat screen TV or anything like that, or flat screen monitors, or even any laptops did not exist. It just did not exist. We didn't have any hard drives at the time. We had a tape drive, like an actual tape, which probably you guys don't even know what that is. But a tape that you would actually have, it was a magnetic tape that we put in to the computer at the very best, right? And some people, I remember even using punch cards. The computer would take in operations, not even through a keyboard, but the interface was a punch card. I enter a punch card into a special typewriter, I would type it out, enter the punch card inside the computer interface, would read the punch card, and then do the operations. So computer interfaces have changed over time, right? And so is software. Software has really evolved. Like it's changed, done a complete reordering. And nowadays, we don't program at the machine level almost ever because it's too complicated for most people. Think about it as like this. How many of you know how to fix a car? You drive a car, right? You guys drive? Right? If you've driven a car, or if you know someone who's driven a car, they know how to drive the car, but very few people know how to fix the car. And I'm not talking about like change the oil or change a tire. I'm talking about like make the car like from scratch. Could you make a car? It's very hard, right? Well, on the same token, most people don't know the machine level. They don't know how to put the zeros and ones together to talk to the machine, right? They use a higher level language to speak to it. And the higher level language gets compiled down to zeros and ones later on. C# is the high level language. It's that 50,000 foot language. It's way up here, and it talks through several layers all the way down, works through several layers to talk to the machine level, and eventually gets to these zeros and ones. Right. Eventually, right? But usually what happens is there's a whole other bunch of layers that C# moves through in order for us to talk to the machine level, right? So again, we're talking about this is what the zeros and ones might look like, right? A bunch of zeros and ones that mean something. And this is, like it says here, part of the Hello World program we're going to be creating that's been converted to machine code, zeros and ones. Higher than the machine code, there was a language called assembly language, which is one step higher than machine code. And assembly language, what we can do with that is, like I said, there's little short codes, like 3-letter codes that meant something, right, at the time. Like load the accumulator. There's a code that meant that. Or, shift a memory location, shift values into a memory location, right? Higher than that is your low-level computer languages. One of the probably most powerful languages at the time that I learned in high school and in university was C, the original C language, which is kind of like the Latin that we have today in real languages, right? When you learn C, everything else that we learn today is C influenced. Every language pretty much nowadays. That's how popular this language was. There was also a B language, right? And there's also a D language. But those languages kind of faded into obscurity. There are not that many people that use those right now. C language even is a procedural language that we still use to program operating systems like Linux that are written in complete C, 100%.
People
right?
still use it.
Yes. Now, back then, there was no object-oriented programming. It was at the root of programming. We tried to figure out how to program computers or how to code, right? We wrote things in order, and there was very unstructured ways of writing things. One of those unstructured ways of writing things mirrored or mimicked what would happen at the machine level, and it was called BASIC. That was a very basic. It was another high-level language, just like C#, but even more high-level, with commands that are very simple. Children could learn how to use BASIC, and I was one of those kids learning how to use BASIC when I was 10, right? But the BASIC I learned back then had a lot of statements. A language is made up of commands, and the computer reads the language in order. That's why we have these line numbers. If we go back to Visual Studio for a second, I have line number 1 to line number 15. The compiler, the computer program, this Visual Studio, will read each of these lines of code one at a time in order. It'll scan each of these lines of code and say, what does the programmer want me to do? Well, each of these things means something, which we'll talk about, right? So we'll look through each of these lines of code one line at a time. Well, back in the day, it was no different. We would look at one line at a time, and each line was a line of instructions that we would give the computer, a directive to say, do this, right? Store this value in this location. That would be one line, right? And it would do one line at a time. And we also had, back in the day, that was very unstructured. We had a way of going back. Go to this line. Go back. So it would go from line 11, I want you to loop back to line 7. That's what it would be. And we don't have that kind of thing anymore. We can't go to a specific line anymore. It's not about that for us at all. We've gone a little bit more abstract, and we're at a different level than we used to be in programming. But that's how we used to code. We used to code like where we had go to this line, and it would do this command, right? And run this line, run. We'd actually put the command run inside the computer, right? We don't have those commands anymore, right? We wanted to run a subroutine, right? There would be a routine would be like a bunch of levels of code. And if I had a subroutine that I wanted to do over and over again, I would say go sub 100. And that would be the line 100. It would go to that subroutine. And that subroutine, I'm just using terminology you've probably never heard before, but that subroutine is something that would run over and over again. I could use it over and over. There's 3 or 4 lines of code that I would repeat over and over again. We don't do it that way anymore. We use loops, right? So again, very unstructured programming in the original days, right? And then we had this thing called, we worked to the point where everything was procedural. It would run through a procedure, and we could call functions over and over. We created some really cool, successful lines of code, and we could, once we wrote it one time, we could call them and we could use them over and over again. Procedural coding is what it was called. And eventually it moved into something called object-oriented programming, which is where you're going to get to in programming 2, right? But that's how we build up. We build up from the lowest level of understanding about what a language is, right? Which is instructions that we give the machine to do things, to store data, usually in different memory locations. The computer has a bunch of memory at the hardware level, and if you go to buy a computer today at Tiger Direct or Future Shop, it's going to be there's going to be a couple of things you're going to ask for, right? They're going to say, well, sir, what kind of computer would you like? How much money do you have to spend? First question they're going to ask you too, right? And they're going to say, well, I want to buy a laptop. Okay, fine. So what does a laptop have? It's going to have some memory, right? They're going to say, well, our laptop, we can get you an 8 gig laptop, right, with memory, with a terabyte hard drive, as an example, and it's going to be an i5 processor, right? Let's make it an i7. An i7 processor for $9.99, right? And you're like, okay, that's cool. Will that go on the internet? Yes, it will. Will this run the programs that I want to run? Absolutely. It'll definitely do these things. But the memory that we have in our computers, this 8 gigs of RAM, random access memory, is where we store temporary programs, where we're running things in memory, right? And when we write programs, we write our code, right? We write them in this random access volatile memory. When we turn our computer off, program's gone, right? We launch our computer, we have to click on the button to launch the program to make it go. And it goes into this temporary space, this random access memory. So the more memory we have, that memory runs our operating system, Windows. It also runs any other program we put in there, right? Back in the day, right, we're talking about our whole operating system ran on 4K, 4,000 kilobytes, right? 4 kilobytes, which is really low. 4 kilobytes right now is like, I don't know, most watches have like, let's say half a megabyte. If you buy like a smartwatch, half a megabyte. Like the very minimum, like a little calculator has more than this big computer that took up the whole desk had before in the day. Our hard drive space, the storage area, when they say hard drive, they mean where we store our programs, our files, and everything else, right? Our hard drives today are massive compared to what we had before. A 25 megabyte hard drive was this big before, and it was this thick and weighed about 10 pounds, right? No joke. And it was really, really slow. Like we're talking about you waited for that 25 megs to load, and you were happy because if you use the tape drive, it'd be even slower. You're going to die. You're going to watch paint peel when that thing's. You're going to go leave the room and go somewhere else and come back, right? That's how it was. Nowadays, these are lickety-split. They're fast. The internet is faster than our computers used to be, right? So anyways, lots of, why I'm saying all this stuff is there's lots of innovation that's been made over the last 30 plus years, right? That I've been doing this kind of stuff. So you know, our programs, of course, the way we program is different. It's not the same way. We don't code the same way we used to code, right? And our computers can take code differently than they used to. They're much better, right? If I was to go back to my younger self and take my iPhone back in the day, right? People would be like, I'm an alien, right? There'd be no way that I would have that kind of technology back then. That's Star Trek, right? That's like, you know, from space, right? And similarly, 30 years from now, our kids, your kids, are going to come to you and say, Dad, right? Can't believe you're using that computer at school. Now we use holograms, you know, holographs, right? Holographic computers or whatever. They just announced holographics now with Microsoft, right? Like I said, you never know what they're going to do. Maybe it's going to be a chip that goes in your eye. You never know,
It's
right?
probably gonna be even like crazier because technology is moving up.
We don't know,
much faster.
exactly. We don't know. But every technology is based on the other technology. Technologies don't come out of the vacuum. They don't come out of space. They come based on some other technologies. Like if today, and I know I digress, if today we're going to build a teleporter, right, to teleport you, like physically instantaneously from point A to point B, we can't do that. We need to know certain other technologies to make that happen. We need to be able to scan your body at the quark level, right? So you need that scanner, and in order for you to do that, you need all kinds of power. We don't have the power to do that right now. But slowly, we're building up our technologies, all the ancillary technologies, the technologies around the technologies, the basic technologies to create our system. We kind of build up to that, and that's what we've done here with this laptop that I have right here in front of me, and the computer that you have in front of you. Slowly over years, we've built it up. So again, same time, think about how software development has changed over time. We don't do things the same way we used to do. So again, we have this high level language. We do things, and we ask things. We're going to talk about things like reading and writing and adding and all this kind of stuff. And all we're talking about is we're talking about adding things to memory. And each thing we do in memory is taking up a little compartment in that 8 gigs or 16 gigs of memory in front of your computer. It's called a memory location. Think about memory locations as like houses on a street, right? So you have a bunch of houses on a street, and each street has its own little address. Well, each memory location has its own little address that we can call upon. We can say that memory location, number 1, 2, 3, 4, 5, right? That's where we're going to store our value, right there, right? Well, you're not going to say memory location 1, 2, 3, 4, 5. You're going to say, you know, my memory, my variable. And my variable is going to be a name for a friendly name for the memory location. So again, we're going to kind of come up with these reasonable names that mean something to us for each of the memory locations we're going to use for our program, right? And the program has its own rules. The way we do stuff, how we lay out the instructions, has rules. Just like we write things in English. We have grammar in English, right? We have periods, commas, all that kind of stuff. Same thing when we read a command in this computer language we're going to learn, C#. It has rules. It has punctuation. It has what we call syntax, right? So the most common errors that we get as first-run programmers, junior programmers, learners, right, is syntax errors. That's the first problem. We misspell something, like misspelling my name, right? It's a syntax error. It's a finger error. You're going to write something and it's supposed to be ABC and you're going to write ACB, and it's a syntax error, right? Because you're supposed to write it in a certain way that you didn't write it. So that's one kind of error. The other kind of error that comes up once you figure out how to write some code is a logic error, where you think it should do one thing. There's no syntax errors. It's correct. You've written it correctly. But you're not telling the computer to do what you're supposed to tell it to do. You're telling it to do something else. So what you think it should be doing and what it's actually doing are two different things. That's a logic error, right? Usually we write programs to solve a problem, right? 99% of the time we're writing a program to solve a problem. We're not writing a program for fun. We don't sit there and go, hey, buddy, let's get together. We'll have a little bit of drinks on Friday night and we'll write a program. We don't do that. Right? We're writing it because we want to solve a problem. We want to make a game. You know, we want to do something with the program. The code is going to make the computer do things, right? And we get in our mind, there's when we start writing an application, which we're not going to get to in this course, we have to conceptualize what the application is going to do. write all of its requirements down, its business requirements down, and try and write our code to match the business requirements, right? Now again, that's just very high level. I'm not going to
Probably
talk too much
in
about that.
real life, like once you get job, right? Like companies are gonna ask us for things.
There's just going to be time. You have to build up your skill set. Right now, you don't know what to do and all that kind of stuff. Most of you, I'm assuming you don't. Maybe you do, right? But you know, assuming you don't know what to do, first you have to build up your skills, programming skills, and then part of your programming skills is all these other little technologies, like understanding what an IDE is, Visual Studio, all this other ancillary stuff like understanding how to put things up on GitHub, knowing how to surf the web to get help to program. Because sometimes we got to go on the web and get help from Google. Say, hey, I don't know how to do this, Google. How do you do that, right? Because Google is our library today. I don't know how many of you have gone to a library lately. I haven't gone to a library in many, many years, right? I do everything online, right? Like most people. Just don't believe whatever Wikipedia tells you, because that's just, you know, it's not always true. It's written by people, right? So again, so we have this high-level language. We write our rules, and when we're writing our rules, the compiler, which is part of our IDE, part of Visual Studio, translates the stuff we've written and converts it into machine code, right? That's what it does. So the compiler takes our code, ugly like it is, at high level, and scrunches it down to zeros and ones, right? The lower level languages write code that's more efficient in general than high level languages. Okay, so the higher level language you go to, like higher than C#, there's other ones. Scripting languages is a good example, like JavaScript and stuff like that. They're much higher than C#, right? As an example, they write code that when it gets translated into machine code, at some point, goes through many, many, many layers, and because of that, is less efficient than something that's lower, like C, or assembly language, as an example, would be the lowest. We don't write code like that. It takes too long. The higher level, the advantage of higher level code, higher level programming languages is we can write them easier. It's easier for us to understand what they do, right? It's not as cumbersome to write the code. But it doesn't take as long to write the code, but it's less efficient. Some languages, like C# and other really optimized languages, kind of have a balance. It doesn't take too long to write it, and it's pretty efficient. And nowadays, from an efficiency perspective, our machines are so fast, even if you're a bad coder, people can't tell. Because the machine's running so quick, it's waiting for us. 99.99999% of the time, it's waiting for us to do something. Like right now. Computer's not doing anything for me, just sitting there waiting. A lot of the time, what the computer does is wait for us to do stuff. That's how slow we are, right? Compared to what it can do. Back in the day, cycles, how much computer time it took to do stuff mattered. It was really important to make our code very, very efficient. Now, we can get by, and even if we're a little bit inefficient, most people can't tell because our computer's so quick, right? So being at a high-level language, then, is not as much of a disadvantage as it used to be. In fact, if anything, it's an advantage because we can write things quicker. So came the idea of this rapid application development world where we can write things in a very quick way with a lot of tool sets and drag and drop functionality inside of our IDE. If you'll notice, when we get to running things with Visual Studio, there's a lot of dragging and dropping we can do to write code for us, right? Okay. I'm almost going to take another break in a second because I've talked a lot. And I see you guys glazing because I'm lecturing now. I'm in my lecturing mode, right? I feel like the old Greeks, like back in the Colosseum. Okay. So we talked about syntax error. We talked about how it translates machine code, high-level code to machine code. Programming logic, we talked about how a computer will execute things one at a time in a procedure. It has its own procedure for running each line of code one at a time. It scans through the code, interprets what it says, and runs things through. Like step by step is what I want to say, right? And when we talk debugging, we're talking terminology here. Debugging is the process where we take a look at the problem. We see that the computer has a syntax error or a logic error and try and figure out the problem. Part of what we do with debugging is called trouble isolation. And you may have heard that before, maybe you haven't. But what we do is, I'm just going to pull up another program for you to figure this out here. I'm going to use Sketchbook Pro for a second so we can draw together. So here's Sketchbook Pro, another application. And let's suppose that we have this big piece of code. It's like this big block of code right here, as an example, right? And inside this big block of code that we have a problem. It's causing an error. We don't know where the problem is. So what do we do with the code? Well, first of all, we're going to get some kind of error in the console. And usually the console is going to be like a little application that comes up that says error, right? It's going to come up like this. It's going to say, here's my error, syntax error, right? And here's my little syntax error. It's going to come up. Look, I even spelled it wrong. I haven't spelled it wrong. I love it. This is stuff that we want to try and avoid. In fact, what I'll do is I'll redo that because I spelled it completely wrong. Syntax error. There we go. And I'll move it around. So here's where the syntax error comes up. And it says, hey, there's a problem. But it doesn't tell you where this problem is. It just says there's a problem. And sometimes it'll say line 71 or line 31. Sometimes it won't tell you that at all, depending on the kind of code, right? So we start looking at the code, and even if it tells us it's in here somewhere, we don't really know where it is, right? We don't really know where it is. So we start trying to isolate the problem. So we start saying, well, it's not up here, right? Can't be up there. And maybe it's not down here, right? We kind of isolate it from there. And it's probably not in here. So where could it be? Where do you think it could be? What other areas could it be? Here or here. Two possible areas. So now we start working to try and isolate. We look in here to see if the problem's in here, in this part of the code. And we isolate this problem. We say, no, it's not probably in here. So it's probably going to be in here. And then we keep doing it. We keep on chopping this code up smaller and smaller until we figure out that it's got to be here. There's no other place to be. It can't be here, here, here. We tested all these other areas. We removed areas of code. And we can do that too with comments, which we're going to see later on. And we've isolated the problem to be right here. This is called trouble isolation or problem isolation. And we need to do that sometimes. Doesn't matter whether if you're at home and you have a girlfriend or your wife and she says something like, hey, I don't know why, but my light doesn't turn on, right? Well, that could be a bunch of different things. It could be that the light bulb's burned. So you're going to say, well, let's test the light bulb. That's the first thing I would test, right? The light bulb, if I replace the light bulb, is it good, right? Put the light bulb back in, doesn't work. It's not the light bulb. Now it's really serious, right? What about, is it plugged in? Check the plug. Yeah, it's plugged in. It's not the plug. Right? Let's plug something else in there and see if something else lights up. Plug something else up there. It lights up. You know it's not the plug, the actual outlet. It's not the outlet because I know I can plug something else in there. It works. Trouble isolation. I'm trying different things out, right? And then, okay, so the plug doesn't. It's not the issue. This other device can work. My lamp, I know it's a new light bulb. Let's try another light bulb, just in case. Maybe this light bulb's burned out too. Try a new one. I go to the store and get a new one, put it in. Still doesn't light up. Something's wrong with the lamp. Could it be that the wire inside the lamp that connects from the outlet actually to the little lamp part is cut? Well, I could take the lamp apart and check the wire to make sure it's okay. Most of us don't do that. We're just going, this damn thing is broken, throw it out, get another one. Right nowadays in our consumable society. Or we can actually check inside the top part of the lamp where it connects from the light bulb into the receptacle, right? We can check that too. But overall, that's what we're going to do. In real life, we do that kind of stuff all the time. We're trying to figure out where the problem is. Well, it's the same thing when we do programming. We try and do trouble isolation to figure out where we have our error. And sometimes we can't figure it out. And that's why we have source control, GitHub. When you go, it worked before, I'm going to skip back to that earlier version of my code that I wrote yesterday that worked, and now I added something new and it doesn't work, and I don't know what I did because it should work and we can't figure it out. Yes?
Can't you just every 5 lines you run your code to see if it works, just so that if you do mess up you don't have to go so far back?
I love your thinking. Yes, you could. You can go back and sit there and run it very often. It's called testing often. You can certainly test
Well, it's
often.
efficient because then you don't have to go look back to a lot of code. You just have to look back to 5 lines to see what you did.
This is cool if you're looking at a small program. But what if your program is many files, and you've added like 5 files since the last time you saved, right? And each file has like 100, 200 lines, right? It's going to be hard to isolate where the problem is, right? So you have to start cutting things out. That's what I'm saying. That's why I showed you. Trouble isolation means we have to comment lines out or take whole areas of our functionality away until the base functionality, we can find that problem. And once we find that problem, we can correct it, right? And the great thing about IDEs like Visual Studio is what they do is they help us. It's not like we have to do it like the old days. The old days, we just had this big, like I said, there was, error, syntax error, doesn't work. And later on, it has syntax error, line 53. And you went to line 53 and you're like, there's nothing here. Like literally would be nothing there. How come it's giving me a syntax error? Well, you have to look above the line or below the line. That's the rule. It's still the same rule now, by the way. If it tells you error line 53 or whatever, a random number, just giving a number, go look there and look above the line or below the line. Sometimes the compiler will know it's around that area they're having a problem. In this case, C# is very specific and it'll say, this particular line, this particular column, and this particular thing is wrong. That's how good C# is and Visual Studio 2013. Like I said, 70 million lines of code to create this, this program to help us create other programs. Okay? Just want to make sure that we don't run too much over the hour mark. I want to take a break around 8:30, like a longer break, 10 minutes, 15 minutes, come back. So let's talk about different kinds of programs. Right? So again, 2 popular approaches to writing programs, procedural and object-oriented programming. Procedural is going the way of the dodo bird, right? It's not something that we do very often, although in some circles it's making a comeback. Procedural means we're going to write a series of steps, A, B, C, 1, 2, 3, whatever, and the program, the compiler, or the visual, our environment is going to just run each step one at a time, right? And that's what it does. And what we're going to do is we're going to write a series of steps and we're going to create variables, friendly names for memory locations to store data. That's what they are. And we're going to just access those variables in a series of steps and manipulate that data back and forth. That's what we're going to do. And that's what procedural programs do. Now, I'll be honest with you, that stuff doesn't happen very often anymore because procedural programs are not as efficient these days. They're not as powerful as object-oriented programs. So we want to get you up to doing things in an object-oriented fashion. For now, though, you're going to do things in a procedural way because that's how we all learned, right? And you're going to do things one step at a time to understand what each thing does. Okay, there's something called an identifier. And what it says here is a one-word name used to reference a variable or method. For you guys, that's like gobbledygook. That's what this means. What does variable and method and all that stuff mean? Well, it's a friendly name to describe this memory location like I told you, right? It can be called identifier. It can also be just called variable name. That's what it is. A variable name, and again, here's going back to Visual C# and Visual Studio 2013. I can create one. I'm going to put this one. You can follow along with me while I do this. I'm going to create a variable, not here. I'm going to create a variable name inside these braces, right? And by the way, I'm going to give you some specific names for these braces. This brace, from this opening brace to this closing brace, I'm going to refer to from now on as a code block. Opening brace, closing brace. How many code blocks are in my program? Take a look at your code in front of you. How many code blocks are in your program? How many?
6.
There's opening brace and closing brace makes 1 code block. How many code blocks are in your program? How many? 3. There's different code blocks, right? However, 1 code block is nested. When we talk about nesting, it's inside of another code block. Like this one is positioned, that's inside this code block. And this one is positioned inside this code block. Similarly, this one, because it's inside this one, is also inside this one, right? Each code block, there's different levels here we're talking about. Here's the outer level. This is the very outer level, this part here. That's the namespace code block. That's what it's called, the namespace, right? And then inside the namespace, there's the class level. That's that code block, right? And inside that class code block, there's the method level, which is this code block. Each code block, right? Think about it as a container, right? Each of these containers can contain variables. Variables are friendly names for memory locations. So if I create a variable inside this main code block, right here, and I'm going to name it, I'm going to give it a friendly name, I can call it whatever I want within some reasons. We're going to talk about some best practices here. But the first thing I got to give my variable name is I got to identify it as a type of variable. There's different types. If I'm going to store a number in this thing, what kind of number am I going to store? Now, for math, if you guys remember, there was integers. Integers are whole numbers, right? They're positive or negative, typically, or 0. That's what an integer is, right? So that's one type of number. The other type of number is a floating point number, right? Or a rational number with a period, a decimal point, a decimal number. Decimal numbers have, there's a rational part, which is the integer, like 1. And then there's a decimal, and then after the decimal is the irrational part, or the decimal, the fraction, a fractional number, right? That's called, in computer language, is either called a floating point or a double. That's what they're called. It's a type of variable that we're defining, right? So before we use a variable, I have to declare the variable. I have to tell the computer that this memory location that I'm calling, this my little fancy name, it has a type. It's going to hold a type of variable. It's going to hold a type of number. I can't just store any number I want. I have to be very specific with C#. There are other languages that don't care. You store whatever number you want. And the type is number. JavaScript is that kind of language if you're programming on the web. It doesn't have, it's a very loosely typed language that doesn't care what kind of variables, what kind of data you put in your variables. You can put strings of characters in there. You can put numbers of integer or floating point or whatever. It doesn't care. And if you can redeclare them over and over again. It's very loosey-goosey. Programmers hate that kind of thing. Programmers like strict control and rules. And if you're going to be a coder, think about yourself doing things in a very strict manner, right? So here we are. We're going to declare our first variable, and we're going to declare it as an integer. Integer, we're going to use the keyword int. Now, if you notice, when I type, this fancy stuff comes up here, right? This little pop-up that comes up here. This pop-up is called IntelliSense, Microsoft's IntelliSense, which is Microsoft's very basic way of doing, or very awesome way, actually, I should say, of doing code hinting. It's giving us examples, a pull-down menu, right, of different other kinds of integers we can use. And I just typed int with lowercase int, right? I got int16, int32, int64, interface, int2, int ptr, a pointer, UI int, a UI int32, different kinds of integers. And at the very, if I keep scrolling down, there's a UI int64 and a UI integer pointer. That's what that is. It's all kinds of different things here that I can pull down. All I want you to do is use the first one. So if I click away, I have int. So it's integer. It's I'm defining a memory location I'm going to use, right? That can only be a positive or negative whole number or 0. I can't put any other kind of number in there. If I try, it's going to give me a syntax error. Okay, if you notice, I have this little squiggly. The little squiggly says, I'm expecting a semicolon, because every line of code we write has to end with a semicolon. This goes back to the days of C programming. C programming languages and PHP, JavaScript, a lot of the web languages we do, any C-influenced language nowadays ends with a semicolon. Some of them that don't are, for example, there's a program like, for example, Python doesn't need semicolons, and neither does a new language from Apple called Swift, right? But most languages that are C-influenced, they need a semicolon to end the line, to say, I'm done with my command. This is what I'm telling you to do, computer, and you're gonna, when I put my semicolon, that's the end of the line. All right? So I got to put that in. So I'm going to say int space, and I'm going to type in my friendly name for the variable. I'm just going to call this my variable. And I've written it in a very specific way. My variable is a lowercase m and a capital V. There's two words here, my and variable, and this is called camel case because you got a bit of a hump where that's where it comes from actually, where the capital is. See, there's this part of the camel, and then the capital letter is the hump. That's what we call camel case. There's also something called upper camel case, like this one, where it's all capitals, right? All capitals are reserved for classes, like program, and main methods, and things like that. We don't use upper camel case starting our identifier, our friendly name, with a capital, unless it's a special type of thing we're trying to do. Usually we do camel case like this, a lowercase followed by an uppercase. When we have two words, my variable. Okay, I'm going to assign this my variable. I'm going to use an assignment operator. I'm going to use the equal sign. That's an assignment operator, right? The equal sign says my variable is going to be equal to, that's how we speak. When we say my variable equals to what, we're going to assign to it 0. Does that mean that it has no value and a semicolon at the end, right? It does not mean that it doesn't have any value. 0 is a value. It's an integer, right? It's not a positive integer. It's not a negative integer. It's 0. So it qualifies as an integer. Now I get this funny green line, my variable. And what those funny green lines are in Visual Studio is a warning. It's telling you, hey, look what it says. The variable, my variable, is assigned. I assigned it a 0 value, right? But is never used, right? I haven't used it. So it's a useless variable. I've assigned the value, I've put some data in the memory location, but I'm not doing anything with it. It's just sitting there, right? And until I do something with it, it's going to give me this warning that says, warning, you defined a variable that's useless. You haven't done anything with it. Okay, this is all fine and good. Let's change this variable. Let's make another variable. So I'm not going to use an integer nowadays. There's another one that's also common that we're going to see a lot of as we program over the next course of weeks together, called string, right? So we're going to write a string. So we're going to say string. And a string isn't like a string that we tie things together with. A string is a string of characters. And a character is a single letter or number. Okay? It could be a letter, a number, or other kind of digit that we can add in. Okay? String. And we can, we're going to make a new identifier. What am I going to call it? My string. My string. Right? So string, my string, is equal to, and this time when we define strings, we have to use the quotation. That's one of our syntax rules. We're going to open a quotation, and we're going to say, hello world, with an exclamation mark and a semicolon. Yes?
You pressed something so that your quotation marks open both of them.
I just pressed quotation once.
You did?
Microsoft IntelliSense
Oh,
made it happen for me.
Okay, yeah,
If you start writing, you'll see what I'm talking about.
I use Notepad++.
Notepad++ is not an IDE. Notepad++ is an editor.
Yeah,
We're using
I use that program.
I love it, and that's good that you know how to use that. Here we have advanced IntelliSense.
Yeah, that's good.
Code hinting that's going to help us. And you know what? Some people have there's an argument. There's two camps. There's one camp that says, wait a minute, if Microsoft IntelliSense or code hinting helps us write code, do we really know how to code? Right? In the old days, there was no code hinting, and you had to know, you had to remember the commands, right? If you didn't remember the commands, you couldn't code anything. You had a handbook, you might have a reference card, right? You have to remember the commands. There's no code hinting at all. Now everything's code hinting, right? So if you notice, I wrote it like this, string, my string. So I have to declare the data type first, right? Which I'm saying it's a string of type string, right? Which means this location in memory, which the friendly name that I'm using is my string, is going to hold a string of characters and a space and an exclamation mark. These are all legal characters to put in my string. It's going to be called hello world. We see it as hello world, right? But right now it's just in the memory location string. This memory location, my string, has a value. We say it has a value of hello world. Okay. So two different types of variables I've talked about right now, actually three. I've talked about strings and integers. I've talked a little bit about decimals or floating points, and there's others that we're going to explore. But the basics of what we're doing here is what I've just done. This line 13, if you look up here, is my real first line of programming, of code that I've written with you guys, right? This line 13 tells the computer that the variable myString, the friendly name myString, right, that points to a memory location we don't know about, right? We don't care about, actually. We don't care which, remember, do you care which real 1, 2, 3, 4, 5 or 5, 6, 7, 8, 9, what memory location is going to be sitting here? No. The answer is no, you don't care, right? Not at this high level. If we were programming in machine code, yeah, you'd care. Because every memory location is, you have to know where the memory locations are held. Now we don't care, and this way we can program faster. Let's pause it there, and let's take some 10 minutes or so, 10, 15 minutes. I think, is Tim Hortons closed now? It's 8:30.
Yeah.
Darn. All right.